Right. Hello, everyone, and welcome to Permafrost Day at the Cryosphere Pavilion. Today's program will explore the local and global implications of thawing ground in the Arctic permafrost region. Our first session, entitled What Everyone Should Know About Permafrost Thaw, breaking down the science and global impacts of global warming, will cover the permafrost basics, carbon content and thaw trends, discussing mitigation efforts, emission monitoring, and the impact on ecosystems and Arctic communities. We are honored to have permafrost experts Gustav Hugelius, Claire Treat, and Sue Natali here presenting with us today. And following the presentations, we will open the floor to questions. So thank you everyone so much for joining us. And our first presenter will be Dr. Gustav Hugelius. He is a professor at the Department of Physical Geography, the Vice Director of the Bolin Center of Climate Research, the co-lead of the Research Unit Landscape, Environment, and Geomatics at Stockholm University. Dr. Hugelius.
Thank you very much for that kind invitation. So I'll start out talking about sort of broad scale issues relating to permafrost and its role in the global carbon cycle. Also talking a little bit about how it was included in the last IPCC report. So I actually want to start with a graph showing the full global carbon cycle. This image is a couple of years old, but I think it's a nice graphic, and it just illustrates all of the major pools of the global carbon cycle. On the top right corner, you have the atmosphere, which is now actually closer to 900 petagrams, and sort of down to the bottom left, you have the soil carbon pool, which is the largest really reactive carbon pool in the Earth system. And then you have these large arrows that shows fluxes in and out of ecosystems. And in the global context, the permafrost carbon feedback really influences the arrows between the soil carbon pool and the vegetation pool and the atmosphere. So we can view it as a subset of that system in a global carbon cycle context. A few of the key take-homes from the IPCC sixth assessment report on carbon cycle feedbacks in the Earth system. They find and they state clearly that carbon cycle feedbacks will increase with warming and will become more uncertain with warming, meaning that our projections of the carbon cycle feedbacks become more and more uncertain under warming. And they also note that there are some really large feedbacks that were not included in the CMIP6 models, the models that the sixth assessment report used to assess future impacts, and they will cause higher CO2 and methane emissions. And the biggest ones that they really call out are wetlands, permafrost thaw, and wildfires, all very relevant to sort of the northern high latitudes. And what this means is that the Earth's sinks, the natural sinks, will become smaller and smaller, and at a more rapid pace. This graph summarizes different pathway scenarios. So you have the emissions of CO2 equivalents in gigatons, sort of upwards, and then you have the different emission scenarios on the x-axis. And the shaded colored areas show you how much of the human emissions ecosystems will take back up. So the ecosystems are doing us a major favor in assimilating a lot of the CO2 that we release, either in ocean or on land. And what we see here is that the less we emit, the larger portion of what we emit will be absorbed into ecosystems. Unfortunately, because a lot of the feedbacks are not included to the models, these sinks are probably overestimated. They are not this big in reality if you include the permafrost and fires and wetlands. So if you look at, this is the IPCC estimate of those carbon cycle feedbacks that are missing in Earth system models. You see the radiative forcing on sort of extending to the right here. All of these are warming feedbacks, and it's fire CO2 response to climate, permafrost CO2 response to climate, permafrost methane response to climate, and wetland methane response to climate. So the IPCC report did, even if they're not in the models, they did try to make an estimate of how large these feedbacks might be. And it equals something between 5 and 10% of the total human change in radiative forcing, just from these feedbacks alone, that are not in the models. So now then, we'll zoom in a little bit on the permafrost carbon feedback. I like this image because it's illustrative of the scale of the problem. You have this massive looming wall of permafrost thawing in the background, and you have a person in the front for scale. And basically, the permafrost carbon feedback is that as global warming thaws permafrost, greenhouse gases are released from organic matter that has been locked in permafrost for thousands of years, and then when this is thawed, it's available for decomposition by microbes, and as a byproduct, they produce CO2 and methane. In addition to the global carbon feedback, there are also a lot of very concerning effects for local ecosystems, direct impacts to infrastructure, ecosystems, and humans living in the Arctic. So we're mainly talking about northern hemisphere permafrost. That's where the largest extent of permafrost is. This animation shows you the shift in permafrost extent that we've seen in the last 20 years. Permafrost still covers a really large portion of the northern hemisphere. It's roughly 15 million square kilometers, depending on how you count. So that's about three times the size of the European Union. But it is rapidly thawing, and this is projected to increase. The rate of thaw is predicted to increase a lot more in the coming decades. So as you see here, permafrost is disappearing mainly along its southern edges, but more concerning is that if you look at the actual warming of the ground, the permafrost warming is actually most pronounced in the north. So in the continuous permafrost zones of Eurasia and North America, you actually see the strongest warming trend. So this is the warming trend at 2 meters depth, as projected by a sort of observational-driven climate model, and you see very strong warming trends of the permafrost, especially in northern Eurasia. This doesn't mean that it's fully thawed yet, but it means that it's warming and approaching the thaw boundary more rapidly. And we're concerned with permafrost thaw because of the carbon feedback, because it contains massive amounts of carbon. Frozen into permafrost is like more carbon than if you combine the atmosphere and all living vegetation together on Earth. So this is a bubble plot where the size of the bubbles are proportional to how much carbon is in that storage. You see the atmosphere, almost 900 gigatons, vegetation, about 500. And the round pools in the middle, you have global soil carbon, about 3,000 in this estimate. And then roughly half of that, or 1,500 or 1,600 gigatons, is actually in the permafrost region. So this is a massive pool of carbon. And if even a portion of that is released into the atmosphere, it causes quite large shifts in radiative forcing. So the IPCC did assess this in the last report, even if it wasn't in the models. They made a sort of literature-based assessment, and they find that between 14 and 177 gigatons of CO2 equivalent will be released for every degree of global warming. So you see this graph here shows the total emitted CO2 equivalents from permafrost by the end of this century under different warming scenarios, 1.5, 2, and 4 degrees. And on the right-hand side, you see, for reference, the amount remaining in the 1.5 to sort of stay under the 1.5 warming of that mission budget. So this is, these are concerning numbers. Roughly 100 gigatons CO2 for the 1.5 degree goals, going up quite rapidly with 2 and 4 degrees. Unfortunately, this might not be the full picture. There are also processes that were not really accounted for in the IPCC numbers. One of them, the major one might perhaps is what we collectively call abrupt thaw processes or thermokarst processes, which are basically when you have a lot of massive ice in the ground. The ground is not just soil and carbon, it's also a lot of pure ice. You see the corner of an ice wedge there in that image. And when this thaws or melts and drains away, the land surface actually collapses. So over time, you get a sequential lowering or change of the whole landscape. And the post-thaw environments that you get after these types of abrupt events are usually quite strong sources of greenhouse gases. And if you add all of this together, you get, on top of the black IPCC numbers we saw before, if you include the abrupt thaw numbers in purple, you get much higher fluxes, much higher projected fluxes, if you include these processes that were not then accounted for in the last IPCC. And yet another concern is if we think of, which is looking ever more likely, overshoot scenarios where we shoot over 1.5 or 2 degrees and then go back down. The problem with that, so you have in red, there's an overshoot scenario, and in green is a better scenario where we just stabilize, right? Whatever the target temperature is. And there are two quite big problems with this. The first one is that because permafrost and other feedbacks drive even further warming, we're going to shoot over even more than we predicted. And the second big problem is that because a lot of the permafrost thaw, once it's triggered, once you have this landscape collapse and local shifts, these landforms will actually not quickly refreeze, and they will keep emitting CO2 or methane for quite a long time, decades to centuries, depending on what landforms you have. So you have a partly irreversible permafrost loss that will actually keep emitting CO2 and methane for a long time, that is triggered during overshoot. So this graph includes estimates if you include abrupt thaw and also then add overshoot emissions as per some model scenarios from a recent paper. And then we are really seeing rather high emissions, especially if we overshoot by a full degree. And then sort of one of the, so it's, as you see here, now we've actually removed the 4-degree scenario, and we just have 1.5 and 2 here. So even if we would cap at 1.5 degrees warming, or if we would land at 1.5 degree warmings, if we overshoot that target, the cumulative permafrost emissions will actually are predicted to exceed 400 gigatons of CO2 equivalents by the end of this century, but in cumulative emissions. So then we're looking at permafrost emissions alone that would be roughly equal to what the EU is emitting now every year. That we would be sort of locked into for quite some time. And then the final point I want to make is that permafrost it's a large system, and it's a system that responds relatively slowly to warming. But this also means that once you've triggered thaw, and once you've sort of woken the system up, it will actually keep emitting for a really long time. So even if we cap warming at 1.5 or 2 degrees, the projected warming scenarios that we see coming from long-term model runs, they persist all the way to 2300, and in some cases even longer. So you see here that we have large emissions by 2100, but we have continued sustained large emissions for several hundred years, in this case up to 2300, which means that we are, even if we're capping warming this century, we are committing 5 or 10 future generations to have to deal with these emissions, and meaning that they will have to implement negative emissions for a really long time to tackle this problem. So sort of key take-home messages. We do see that evidence that the permafrost region is actually already a net source of greenhouse gas emissions, and we're already committed to profound permafrost thaw impacts, even if we would cap warming now relatively soon, which means that we're decreasing remaining emission budgets, and we will be affecting several future generations for these emissions. And we also see that abrupt thaw processes create local scale irreversible tipping points that transform ecosystems, damage infrastructure, and greatly increase volume. And we also see that overshoot warming scenarios would trigger irreversible permafrost thaw that would drive additional warming for centuries, even after the climate stabilizes. Thank you.
Thank you, Dr. Kubelius. And up next, I'm happy to introduce Claire Treat. Claire Treat is a research group leader in the permafrost research section at the Alfred Wegener Institute Helmholtz Center for Polar and Marine Research. Claire?
Thanks, Abby. All right, so thanks, Gustav, for setting us up really nicely with the introduction to permafrost thaw. So I'll talk about how we can actually quantify these carbon losses. So here we have an example of thawing permafrost from Siberia. And we know that as the system thaws, it starts to emit greenhouse gases, both as CO2 and as the more potent greenhouse gas, methane. But if you look at this picture and try to imagine actually making some measurements there, it's a bit challenging because this is a really dynamic system. The edge of the cliff is eroding. There's all this mud flow in the bottom. So how would we actually get these greenhouse gas flux measurements? Similarly, here we've got another ecosystem with thawing permafrost from interior Alaska, where we can see the areas of intact permafrost uplifted and recently thawed permafrost in the inundated areas. And again, here we would expect them to be releasing both CO2 and methane. So how can we measure or quantify this carbon loss that we see with permafrost thaw? There's two main ways that people are using. First are the eddy covariance flux towers. So these systems measure CO2 and methane fluxes on a continuous basis and then back calculate, so you get measurements of CO2 and methane fluxes in a continuous record at a region surrounding this tower called the footprint. So this can range from anywhere in scale of 10 meters to probably about 100 meters. Another method for measuring greenhouse gas emissions in thawing permafrost is to use flux chambers, either automated chambers like the one shown in this picture, where the top lid closes automatically to measure the change in concentration of greenhouse gases, or manual ones that your students carry around the tundra so that they can capture spatial variability among vegetation types. So when we start to aggregate these individual sites where we measure on permafrost, where we measure carbon emissions, we can start to get a picture of how permafrost emissions are occurring across the landscape. So this is a figure from a recent census. We see a map showing the distribution of sites that are measuring CO2 emissions within the permafrost zone. Currently, there's about 188 sites that are actively measuring CO2, but these are all not all located on permafrost. The colors in the map are indicating whether a particular climate region or climate zone is well represented by the measurements. So in areas like Fennoscandia, where we see here at my house, so areas like Fennoscandia, there's relatively dense data coverage, so these are pretty well represented. Whereas in a lot of Arctic Canada and a lot of Siberia, there are relatively few measurements and a lot that we can't extrapolate spatially in order to determine what these CO2 emissions are across the board. So when we've analyzed what these CO2 towers, the tower network that we have looks like, we can see that some areas or regions are better represented than others in terms of their tundra and Arctic area. So this is a figure on the left showing the percentage of observations, and on the x-axis showing the percentage of area within the tundra regions. And so the regions above the line have a relatively high number of observations compared to the area that falls within the tundra permafrost region. So this includes Alaska and Finland, as well as Sweden. On the other hand, Canada and Russia have a relatively low number of observations compared to the area. We also see a difference in where these towers and measurement observations are placed. So they tend to be placed in evergreen needle-leaf forests, whereas in reality, across the Arctic and boreal zone, there's actually a lot more of deciduous needle-leaf forests. It's found, then we actually have measurements in. Similarly, sparsely vegetated areas are really poorly captured. The other thing that's really difficult to do with the measurement network that we have now is to determine temporal trends in CO2 emissions from the permafrost zone. Currently, there's a relatively high data latency, so it takes a minimum of a year to basically finalize and publish the eddy covariance flux data, so it's really hard to know what happened 3 months ago and if you saw changes in CO2 emissions associated with a warm event, say extreme heat wave, that kind of thing. One thing that's promising is this example from Ted Scher's group at 8 Mile Lake, where they have a provisional system developed and they report their data every 3 months, even though it's only provisional. So in the future, we would like to see systems, large-scale measurement systems that can give us near real-time emissions that could be used to predict gridded and temporally resolved CO2 products that we could compare to models. And this is really also important to do because you can pretty clearly see that CO2 emissions from this site have been increasing over time. And on top of that, there's a seasonal trend associated with the uptake. Methane is another important greenhouse gas emitted in the permafrost region. There have been several recent syntheses efforts, including the bald methane synthesis and the FluxNet methane synthesis, as well as an earlier one that I did on winter emissions. So we know that these northern sites within the permafrost emit somewhere between 25 and 32 teragrams of methane per year. However, again, we have really limited sites with continuous measurements, so it's really difficult to upscale these to get a picture of the Pan-Arctic methane budget. So this is an example from a Finnish group using all the data that they could find for methane fluxes and then trying to upscale the product for the permafrost region using statistical methods. And really most important for methane emissions are the two largest wetland areas, the West Siberian lowlands in Russia and the Hudson Bay lowlands in Canada. And you'll notice represented here are the sites where they actually measure methane emissions by these points. And there's maybe one site located near the West Siberian lowlands and nothing in the Hudson Bay lowlands. So this is really challenging and problematic when we're trying to quantify the permafrost region methane budget. In addition, we have lots of manual chamber measurements. These have been done for much longer, but they're really patchy and sporadic in space and time. So we have a challenge to integrate those into our data sets. So to summarize, some of the challenges that we have to make measurements in the permafrost zone are access. So a lot of these areas are really remote off a road network with limited power, which makes both the installation as well as the regular maintenance that these sites need difficult. In addition, the site conditions tend to be difficult with cold and dark conditions, with snow, ice, and wind that tend to damage equipment. And overall, this has contributed to our really sparse observation networks. We also have relatively few long-term data sets for both CO2 and methane emissions, which are really problematic when it comes to trying to detect changes in CO2 and methane fluxes that we would expect to see with warming and permafrost thaw. Also, we have this problem of data latency and immediate processing that we would like to get resolved. So for solutions, I think one solution is to start to operationalize our existing greenhouse gas flux monitoring networks. So this would include FluxNet and ICOS sites. And so there's an existing initiative, the WMO Global Greenhouse Gas Watch, I think can provide the framework to help to start to do this and integrate these various types of measurements. But of course, these require commitments from the countries to doing this. I also think it's important to continue to develop new technologies that are suitable for measurements in Arctic conditions. So those that can operate autonomously, those that consume less power, those that require less maintenance. I think also, actually on this last point, I think there's some promise with a new crop of methane sensors that are coming out, and CO2 sensors that we may be able to improve on these in the future. I also think it's really important to develop additional local partnerships with communities that are working in these areas and that know these areas, that we can find people to help do the installation, the operation, and the maintenance. And this is really key for being actually able to continue to collect this kind of data. So that all ends. Thank you.
Thank you so much, Claire. And with that, I'm excited to introduce our final presenter today, Dr. Sue Natali. Dr. Natali is a senior scientist at the Woodwell Climate Research Center and the lead of the Permafrost Pathways Project, a collaborative initiative that seeks to harness the combined expertise of leading research institutions and on-the-ground organizations specializing in climate science, policy, and environmental justice to inform and develop adaptation and mitigation strategies to address permafrost thaw. Dr. Natali?
All right. Hi, everyone. Thanks for being here. I'm going to switch gears a little bit and talk about the on-the-ground impacts of permafrost thaw and what that means for folks who are living on permafrost in terms of decision-making in response to climate change. And just in thinking about the previous two presentations, I think what we know here is there is some uncertainty when it comes to the magnitude of the feedback from the permafrost region, but we know there is this range. We know that permafrost is already thawing, and we know it's going to get worse. So yes, there is uncertainty, but we know something, and so I want to focus what's happening on the ground, and so I just want to start off by acknowledging the people in the lands where we work. So our work spans, the permafrost region spans Arctic and boreal regions. Indigenous people have lived here for thousands of years. And I want to recognize the harm that Western science and Southern settlers have caused and continue to cause as a part of colonization and extractivism. So as scientists, we aim to conduct our work in more equitable ways by valuing people, by valuing Indigenous knowledge and Indigenous sovereignty. And we are continuously working to improve the way that our science is conducted. And then just to revisit the map of permafrost distribution, this is the current areas where there is some level of permafrost. That map will look very different in 2100. So much of the permafrost is going to be lost as a result of climate warming. This is a map of projected surface permafrost lost in 2100. This is under a high warming scenario. So all the light teal areas, light shading is the areas where it will be lost. The map can look really different, with much more ambitious reductions in fossil fuel emissions in the coming years to decades. So rather than losing 75% of the permafrost, as you see here, perhaps we can limit that to 20 or 25%. And that's important for a number of reasons for the permafrost carbon feedback, but also for people who are living on permafrost. And I'm focusing on sort of adaptation responses to permafrost thaw alongside climate mitigation because permafrost thaw is already underway. And we need a rapid and just response to deal with both the current and the future impacts. So that rapidly massive abrupt ground collapse that you saw in those previous pictures can have serious and at times disastrous implications for communities who live on permafrost. Many of these communities are living in extremely vulnerable environmental conditions where the issue is not only permafrost thaw, but is combined with sea level rise, coastal and riverine erosion, increased storm impacts, and all of these combined at times can threaten people's lives, infrastructure, Indigenous ways of living. And so this is just a picture I like to show as a community in Southwest Alaska. And you can see from this picture, you don't need tens of meters of ground collapse for this community to be at risk. Just even a few centimeters of sinking ground can have serious impacts. And then just a few more pictures of this sort of not only the gradual thaw, but also this abrupt ground collapse. It's often coupled with erosion, and this is causing irreversible loss of land for Arctic communities. So close to 5 million people are currently living on permafrost. In the coming decades, even under low emission scenarios, about 3 million people will be impacted by near surface permafrost thaw. Anywhere from about 10% to a third of those people are located in areas that are considered high hazard areas. So this are people who are living on ground that has a lot of ground ice and that is likely to sink and collapse when it thaws. As we know, climate change comes with a cost. And doing nothing when it comes to adaptation is a lot more expensive than if we take actions to reduce fossil fuel emissions. So under moderate emissions, impacts of permafrost thaw on infrastructure, these costs are estimated at 182 billion. So this is for the entire permafrost region. And that goes up quite substantially. Under high emissions, it's 276 billion. So a 50% increase in costs just for dealing with the cost of infrastructure. And I'd say this is a pretty conservative estimate because it's only accounting for the direct costs of permafrost thaw alone on infrastructure. So meaning that it doesn't account for any infrastructure damage from flooding and erosion that's exacerbated by permafrost thaw. It doesn't account for combined effects of multiple climate hazards, including storm damage from the loss of, say, landmass sea ice. It doesn't account for non-economic damage. It doesn't account for the loss of livelihoods, the impact on indigenous ways of living, the loss of subsistence lands and fisheries, the loss of fish camps, boats, fish racks, and other critical natural and cultural infrastructure. And all of these things are really important when we're thinking about the cost of climate change. We often hear about how expensive it is to deal with it. But I just want to come back to the fact that it's so much more expensive if we don't deal with this. Just some pictures on the ground. These are some of the communities where I work, what it looks like and what I'm talking about when I'm saying these impacts on critical infrastructure. This is a sewage lagoon, 2 sewage lagoons in communities in Southwest Alaska. As the ground subsides, the sort of the protective barriers of these sewage lagoons can be breached, leading to a leaching out of waste into the community and into ecosystems. We're also seeing cases where oil tanks are threatened, barge landings are being impacted by permafrost thaw. Many of the communities in the north are not on road systems, so these barge landings, this access is really a lifeline to many of these communities. Homes precariously perched on sinking ground where the water is accumulating underneath it is quite common. And then also impacts on roadways. In this case, this is a boardwalk community, and you see this sort of tilting and a continual need to be sort of fixing these roads so people can have access. In the state of Alaska alone, there's more than 70 communities that are facing imminent threats from permafrost thaw, flooding, and erosion. So each one of these dots on this map is some of those communities. The ones in yellow, there's through the Permafrost Pathways Project, we have 10 partnering tribes in Alaska who are making decisions about adaptation. And the base layer here is again showing the area where surface permafrost will thaw in the next 30 years. So you can see for most of these communities, they will be losing quite a substantial amount of permafrost. Despite the rapid progression of permafrost thaw that's already underway and the need for climate adaptation to support community resilience, in the United States, there's no centralized climate adaptation governance framework. And I don't think that United States is unique in this. As nations and the international community begin to grapple with this process, it's really critical to ensure that adaptation decision-making is led by the communities that are impacted, and that the decision-making respects Indigenous sovereignty. Many of these communities are Indigenous communities in the North. So this is just a schematic showing how we're, the work we're doing is in this context to support this decision making. And so a central component of our work is co-production of knowledge between Indigenous scientists, Indigenous knowledge holders, and Western scientists to address the impacts of flooding, permafrost thaw, and erosion, and the combination of these hazards known as ushtek. This is a Yupik word, meaning catastrophic land collapse caused by these interacting effects. Scientific community would probably call this thermokarst. We also recognize that none of these environmental hazards exist in a bubble, so adaptation decision-making needs to include social and cultural indicators. It's not just a matter of finding solid ground if people need to relocate, but the communities need to lead this so that these decisions are meeting their cultural needs. And with that information in hand, we then assess the options to support adaptation and resilience. And this can range anything from protection in place, so installation of erosion interventions or raising homes, managed to retreat, or whole community relocation. So through this work, just a few recommendations, and this is just thinking about things on the national level or the US level. So first of all, we need a federally coordinated adaptation governance framework to equitably facilitate decisions of US Arctic communities. We need some formal guidelines for standardizing the integration of Indigenous knowledge into national climate policy and procedures for data sovereignty. Designated funding mechanisms to directly support Indigenous peoples' adaptations, decisions, and actions. In recognition that slow onset hazards like permafrost thaw are part of disaster response policy and response, currently they are not. And then just thinking about this in the context of the international community and recommendations for COP28. First of all, we need rapid and equitable transition away from fossil fuels to renewable energy sources and support for natural climate solutions to reduce permafrost thaw. We need the establishment of a comprehensive framework for the global goal on adaptation that includes adequate means of implementation that are specifically tailored to Arctic adaptation needs, integration of Indigenous knowledge and human rights-based approaches, recognition of Indigenous peoples' right to self-determination. And finally, we call for equitable participation of Arctic Indigenous people who are most affected by permafrost thaw and other climate hazards, which are causing irreversible loss of land, into the operationalization of the Loss and Damage Fund. As you're all aware, I'm sure the Loss and Damage Fund is not focused on Indigenous people of the North, but we have communities that are being severely impacted who are in need of support. And with that, I will stop and open up for questions. Thanks so much.
Thank you so much, Sue. And I would love to invite you three to, if you don't mind moving your chair so we can have some questions from the audience. I also have a whole bunch of questions, but I would love to let the audience have a chance to ask first. So if you'd like to ask a question, I would love to invite you to introduce yourself and then state your question. Please.
I'm Gail Lucas. I'm an emergency medicine physician and one of the fellows at the University of Colorado. I'm working with Alaska Native communities and looking at the intersection of each and their health. Obviously, permafrost is part of this. I was wondering kind of like what y'all were getting at with the intersection of like citizen science and how we kind of expand our understanding of what's happening in Arctic areas. Like what is being done, like how are we partnering with folks? The value of Indigenous knowledge cannot be understated, and being able to empower them to kind of contribute to science with their knowledge, and then also just we have folks on the ground who can bring in more information. And I also with the CIs and all the permafrost thaw, there's a lot of concern about jobs because they're no longer able to get the food that they're used to having, and so like this is a potential place to provide jobs. And has that been a conversation too? Because I know that like with the Willow project and everything, that was very controversial because it provides jobs for folks who are there, and if we can give alternate jobs, like what is that?
I'm happy to comment on it. Yeah, so through our Project Permafrost Pathways, as I mentioned, we have 10 tribes who are partners on this project. As part of that, each one of the tribes gets funding to support a full-time person for the 5-year scope of the project. So I think it's a really key component of this when we're thinking about partnering with the communities One is making sure there's funding to support a person to do their work, because most of the people in these communities are doing multiple jobs already, in addition to subsistence jobs within the communities themselves. And so trying to pull people in to do this extra work is really challenging. And then I think, what was the other part?
Basically just like how folks are being engaged and ensuring that they're being compensated appropriately, and kind of what work are they doing, kind of how are they being involved.
Yeah, and so in our case, the folks we're working with are doing a lot of the on the ground monitoring, and what we do with them is really driven by what the communities need. And so some of the technical work we're doing, some of the people in the community are leading the technical work. It kind of depends. Sometimes there's training, and then they're working with us to take the knowledge of the community, take these kind of technical skills that we're bringing in to put that together. And those things are really needed for the communities we're working with, who are making adaptation decisions, in part for them to guide, to make decisions if we have to move, what's the protection, what's the timeline, but also to help them to access funding, because a lot of this information is needed for the agencies in the US to get some of that thing.
I can just jump in on, and I think that, I mean, you in your answer you highlighted a really good example of how to work with this, but also essentially one of the problems that we have as scientists in that we tend to work on project basis. So we get something that's funded for 3 or 4 or 5 years. While, and I think you highlighted this really well in your presentation, Claire, that the long-term monitoring of whether it be active layer depth, the greenhouse gas fluxes, or whatever, is something that we need. We need long, unbroken time series. And I think ideally this type of monitoring and this type of support also to include local and indigenous people should come from stable funding sources that run over long times. You're able to really work with people for now, this is 5 years, but I think a lot of this long-term monitoring, I mean, the scientists are still doing it on a project basis, and we're all trying to scramble and keeping it alive, but there is a very limited permanent solid funding streams from the Arctic countries to actually maintain the observational networks over a long time. But I think if that is designed and funded, it definitely should and would need to include local and indigenous people as key skill people doing that.
Just to build on that, I think right now a lot of the institutions and the funding schemes are not well prepared to deal with this question. I mean, both with this long-term funding issue, which makes our monitoring sites really vulnerable to changes, but also with this, I'm at a particularly bureaucratic organization. And so it's really difficult to figure out how to get your purchasing department to compensate someone local that you're working with. And I think some of my colleagues have been trying to work within the funding framework, and some of these funding agencies, I think they're picking up on the buzzword, but don't really understand what it actually means, and like that it's maybe not possible and not feasible for local communities that you're partnering with to have someone devoted to doing their grant management and outreach strategy and reporting that's required with some of these grants. So I think, I think there's got to be some sort of change in the system, the funding system.
We have time for one more question from any audience.
I have several questions that maybe more in addition to cooperate. My name is Vera Kuklina, and I'm speaking at NCU, and I already organized the session on permafrost DGU once. And our project is on frozen commons, so we are studying ice, snow, and permafrost, how they are shared here and maintained by communities and other stakeholders. I just wanted to make a remark that there was numbers of 4.9 million people live on permafrost. This number is based only on the Arctic, and if we want to focus on cryosphere, we need to take into account people in other parts of the permafrost regions. And here, my also input that we are working in Mongolia. It's fifth country by permafrost coverage in the world. So it's very important maybe to include future plans, because it's great to cooperate with local communities and also indigenous people out there, and think about how we can build our evaluation. And finally, I would to invite to participate in ICAR proposal for next 10 years plan of studies. I'm working with the group on infrastructure research, and we are particularly focused on development of collaborations with indigenous people, I think how we can study infrastructure across the arts. We are working with IRP and trying to work with other agencies because it's not only, as you already mentioned, it's very difficult and challenging to use only national science foundation or any research foundation to do that.
Thank you. Good point.
Okay, one more question, and that'll be a few minutes before our next session starts, if you would like to hear a little bit more.
Kenneth, you showed on the graph that Permafrost zone is meeting 25 to 30 teragrams of methane. Can you explain where it was used enough from? Does it include this West Siberian and Canadian wetlands? If yes, and if no, then it's actually quite a big flux, and it's current flux. So it's at a time when Permafrost is not really degrading massively yet.
Yeah, so yes, actually, that was from north of 40 degrees.
Can satellites help with solving this?
Yes, I think there's a lot of promise with including the satellite data, but we're not there yet. So they need a lot more validation. And the other problem, particularly regarding methane, is that the current methods, I'm not an expert on this. I'm close to, it's a adjacent field, but the methods that the satellites are using, I think they depend on light. So there aren't measurements during the winter.
Yeah. So they can only measure in the summer, and they're also not like tuned to these relatively low levels of natural ecosystems, right? They're meant to like pick up.
So they can pick up the pipeline leaks, but not the cooling, right?
Yes, I mean, there are full column observations for methane that are being used coupled with inverse model systems, so that you try to track emissions from land into the atmosphere, and you use weather models essentially to sort of back calculate it. And a lot of the inversion models that are being used now globally to do the global methane budget, for instance, are augmented with satellite observations. So they are used, and it does lead to significant improvements, but they don't see the winter time. And still, especially when you have low fluxes or low concentrations, like Sue said, the sort of the source appointment saying you can see the flux, you can see the concentration in the atmosphere pretty well, but methane is a well mixed gas. So it's really difficult still, the smaller diffuse fluxes, to say which part of the Arctic they actually came from is still a very big challenge. So I think the methane concentration in the atmosphere is well known, but exactly where it comes from is less well known.
The clouds are also in the shape too, so it's very cloudy a lot.
All right, everyone, thank you so much for joining us. Thank you to our panelists. And as a reminder, this is our first event of the day here at Permafrost Day. There'll be events for the next couple hours, so if you're free, we'd love to have you. And thank you for joining.